so we're on session 6, which is sequences or the nth term. There's quite a lot of notes here which cover all the specification points. However, a lot of them are in the additional section. I've not really seen them tested. So things like being able to do a Fibonacci sequence or put a geometric sequence into the term, you will typically be asked for an arithmetic sequence, or you might have to recognize things you can put in squares or triangles. So we're just going to start the questions. The notes are here, you can go through them, but I wouldn't worry too much if you can follow the questions. So we're going to find the nth term of this sequence. You're going to first look for the difference. So every time we're adding 4. And we're going to say to ourselves, as soon as we find out what we're adding, we write 4 and then n. Then we say, how do we go from 4 to 3, which is the first number? We minus 1. And that is your nth term. So if we wanted the 50th term, remember 4n means 4 times n. So that's going to be 4 times 50 minus 1. So 200 minus 1, which is 199. Right, let's have a look at the next one. I'm going to do the same thing. What's the difference? It's plus 3 every time. So as soon as we see that, we write 3n. And then we say, how do we go from 3 to 5? Well, we add 2. So if we needed to find the 67th term, 3n means 3 times n, which is simply 3 times 67 plus 2. If we do 3 times 67, we can plug that into a calculator, add 2, we get, we get 203. Sorry, just checking my mental arithmetic. Okay, so now let's look at the exam questions. Here are 4 terms of a sequence. What's the next one? So we're going to go, okay, what's the pattern? We're adding 7, we're adding 7, so we're adding 7 each time. So you're going to do 23 plus 7, 7 plus 3 is 10, so it's going to give us 30. So it's going to 30. Explain how you got your answer. So you're going to say add 7 to the previous term. And so now we can do the nth term. We'll write 7n. Okay, so how do we go from 7 till 2? We minus 5. So the 10th term will be 7 times 10 minus 5, which is 65. Okay. Now we've got triangular numbers. Now all this means is numbers that you can write like a triangle. So we've got 1, 3. The next one you'd have 3 at the bottom. 3, 4, 5, 6. Can you see how that happens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is what they said. So now here you'd end up with 5 dots plus 4 dots plus 3 plus 2 plus 1. So essentially here it's 1, here it's 1 plus 2, here it's 1 plus 2 plus 3, here it's 1 plus 2 plus 3 plus 4. So you're essentially adding one more. So here it's going to be 1 plus 2 plus 3 plus 4 plus 5. So if you know that's 10, the next one you're adding 5, so it'll be 15. Okay, now we're going to match. So this is where we've got some of the strange ones. If you looked at the notes, you'll see a Fibonacci sequence, but we don't need to worry about that. The nth term, the sequence you learn where you add each time, is called an arithmetic sequence. And that's where you've got the same difference each time. Triangular numbers are the ones we just did, which is 1, and then 1 plus 2, which is 3, and then 1 plus 2 plus 3, which is 6, and so on. So 1, 3, 6, 10, 15, well, we know those are triangular numbers. Square numbers are quite easy too. 1 squared, 1, 2 squared, 4, 3 squared, 9, 4 squared, 16, and so on. So we've got square numbers. Cube numbers are going to be times each of the square numbers by the number it was square again. So 1 times 1 times 1 is 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, So we've got some cube numbers there. Then we've got to decide which one's arithmetic and which one's geometric. Now here, every time you're just adding 1. So that's your arithmetic. And here, every time you're timesing 2. So that's geometric. So that's probably quite tricky, but as long as you can use some of them, you can make a sensible guess for some of the others. Okay, so now we've got something written as a rule. We've said the term-to-term sequence is add 8 and divide by 2. So we're going to take minus 24, add 8. So when we do minus and adding, we're becoming more positive. So we get to minus 16. Divide that by 2, and we're going to get minus 8. So that's our first one. Then we're going to add 8 again. Minus 8, add 8 is just going to be 0. We divide by 2 is still 0. And now we've got a different sequence. So we're going to subtract 1 and multiply by 5. So this time it's giving you the third term and you've got to go backwards. So instead of multiplying by 5, you're going to divide by 5. So 120 divided by 5. 5s into 12 go twice. And that's 10. And we've got 2 left. And then we're going to get 24. And then we're going to, instead of subtracting 1, we're going to add 1. So we get 25. So our backwards formula is essentially doing the opposite. So we're going to divide by 5 and add 1. So 25 divide by 5 gives you 5. Add 1 gives you 6. Right. Here is drawing some patterns. So we've got the first 3 patterns in a sequence. And we've got to draw pattern 4. So if you look, you've got a 1 box, you've got a 2 by 2, then you've got 3 by 3. So we're going to have a 1, 2, 3, 4 by 1, 2, 3, 4, all with dots in it. And then without the corners, all the way around the edge, it's coloured in. You will draw it more beautifully and accurately with a ruler compared to what I have. I think it's all filled in, isn't it? And so that's your pattern 4. So pattern 3 has 9 dotted squares and 12 black squares. How many dotted squares will be in pattern 8? So it has 9 because it's 3 times 3, right? So, and 4 is 4 times 4. So pattern 8 will be 8 times 8, which is 64. And then it's saying write an expression for the number of black squares. So if we have a look for pattern 1, there's 4 black squares. So let's just write it in terms as long. Pattern 2, we've got 1, 2, 3, 4, 5, 6, 7, 8 black squares. Then we've got 12 black squares. And if we look each time, we're adding 4. So remember, then we write 4n, because to go from 4 to 4, you add 0, so you don't need anything extra. Sally looks at the patterns. She says, if the pattern is odd, the total number of squares is odd. If it is even, the total number of squares is even. And explain why she is right. Well, if it's odd, then you're going to get an odd number times an odd number. So let's think what we're going to have. So if it's odd, the black dots will be an odd number times an odd number. So if you have an odd number times an odd number, so 3 times 3 is 9. Let's take 5 times 5 is 25. 9 times 9 is 81. Will always be odd. And then to that odd number, you're adding 4 times the number. So even. So then plus the, what do we call them? The black squares. So even. So let's write a sentence there. Sorry. So black dots, odd, odd. and we're going to say the black squares are always even. So an odd plus an even is always odd. Okay, so that works. Now let's think about even. The black dots will be an even number times an even number, which is an even number. And the black squares, because they're a factor of 4, are always even. So black squares are even. So an even plus an even is always even. That's a little bit complicated, and I think that's from the OCR paper. If that doesn't make sense, don't worry too much about it, as long as you can do most of the question, which is above. Okay, so hope that makes sense. Like I said, your notes are very detailed. They take every specification point, including the extra stuff that gets you up to the higher. But hopefully those questions make sense. And yeah, see some of you next week.